So let's talk a little bit more about the Fibonacci numbers again, this time from a slightly different point of view. So recall that we encountered the Fibonacci numbers once earlier when we talked about the Euclidean algorithm. So in the context of Euclidean algorithm for GCD, and there we asked the following question: how should you choose your two numbers so that the Euclidean algorithm takes exactly n steps to give you the answer? Okay, and it turned out that you sort of needed to pick your Fibonacci numbers as your starting, you should choose two successive Fibonacci numbers as your two starting numbers. And we sort of said that the Euclidean algorithm can also be viewed in terms of, say, continued fractions. So let's just do this by example. So recall the Fibonacci numbers are f0 and f1 are 1, and the next term is just the sum of the two preceding terms for all n at least 1. Now the next few terms are 2, 3, 5, 8, 13, 21 and so on, and we could view this Euclidean algorithm, for example, applied to this as a continued fraction. So recall we talked about this earlier. So if you look at 8 over 5, then we think of it as 1 plus 3 over 5 and 5 over 3 and so on. So this gives us 1 plus 2 over 3, which is and that is going to be 1 plus 1 over 2. Okay, so the final 2 could actually also be written as 1 plus 1 over 1. So we can sort of just think of it as a continued fraction, finite continued fraction with all ones in it. So this is how the ratio of two successive Fibonacci numbers looks. It's just a finite continued fraction like this. And so let's just see, the one we wrote out here is, so this was 2 is f2, f3, that's f4 and f5. So this is really f5 over f4, and if you sort of look at how many ones there are in this equation, so you will notice that the ones that sort of appear on the bottom, so there are 5 of them. So there are 5 ones here, and the ones that appear on top, there are 4 of them. So that's these 4 ones. Okay, so this is 4 ones, and here you have 5 ones. So when you look at f5 over f4, that's sort of what you have, the sequence in which you can either think of it as the lower sequence of ones has 5 ones in it, or the upper sequence of ones has 4 ones in it. Okay, and in general, of course, n plus 1 over fn will look similar. You will have the continued fraction. So this is the sequence, the Fibonacci successive Fibonacci ratio. This would just be 1 plus 1 over 1 plus 1 over and so on. Okay, so where this, let us say the bottom sequence of ones has n plus 1, is of length n plus 1. Okay. Now what we want to do is to try and understand what these successive ratios look like. So let us just see what we have for different values of n. So if you looked at f2 over f1, f3 over f2 and so on, or even f1 over f0. Right. So I mean, one can explicitly compute these. So we have, for example, the first term is just 1, 2 by 1, 3 by 2, 5 by 3 and so on. So let's just write out a couple of more. And if you actually computed these values, let us say you put it into a calculator and sort of see what sorts of numbers these are, we notice the following. So, this guy is a 1, this is a 2, this is 1.5. So, I will approximate the others. So, this is say 1.66, 8 by 5 is 1.6, 13 by 8 turns out to be 1.625, 21 by 13 is 1.615, the last term that I wrote out here is 1.619 and so on. So, you notice the following feature, that the terms sort of oscillate in value. So, you have got a bunch of terms which are, so if you look at these ones, 2 is more than 1.66, more than 1.625, more than 1.619 and so on. So, these terms sort of decrease in value as you go along, and the other sequence of terms, so which is the 1, 1.5, 1.6, 615 and so on, increase in value. Okay, so, there is sort of, you can view this as somehow being these two different sequences, sort of the even ratios and the odd ratios sort of glued together, and one of them sort of decreases in value, the other increases in value, but it seems like they are sort of slowly converging to something. So, the as we look here, we are already, the first two places, decimal places are sort of already 1.61 in both these, and so this is, it oscillates quite a bit as if you compute a few more terms, but here is the interesting statement. So, if for example you try to draw a graph of these ratios, so this would be an instructive thing to try and do. For each value of n, sort of plot what the ratio fn plus 1 over fn looks like. Sort of oscillates, but with smaller and smaller peaks and valleys till it sort of approaches a limit. Okay. So, it turns out that if you sort of look at what happens as n goes to infinity, the value, the y axis value is some number L. So, it approaches a limit L, and in fact here is the exact graph how it looks like if you actually plot the values. Okay. Okay, so of course this is at this point just something we are observing by looking at the graph itself. It is not really a proof, but what we are claiming is the following is, so this is really the statement that the limit as n goes to infinity of fn plus 1 over fn exists. Okay. And for the moment let us just assume that this fact is true, and assuming this is true, let us see what that limiting value has to be. Okay. So, observe that, so for the moment let us assume this proposition. Now, let us try and compute the value of this limit given this assumption. Okay. So, let us call this limit something, let L denote the value of this limit. Now, observe that because of the way the Fibonacci numbers are defined, if you compute the next term of this sequence, so if you look at what fn plus 2 over fn plus 1 looks like, this is, well, you can just write out the definition. This is fn plus 1 plus fn divided by fn plus 1, and you can rewrite this as 1 plus 1 over fn plus 1 by fn. Okay. In other words, if you denote the terms of this sequence, if you just call the sequence terms as an equals fn plus 1 over fn, then what we are claiming here is that, so this can be rewritten as an plus 1 times an equals 1 plus an. Okay, and now what we will do is we will take limit on both sides of this equation. So, I have got limit of an plus 1 an equals the limit of 1 plus an. Observe that the limit, so recall properties of limits which say that if I have two sequences, then the limit of the product sequence, that is a sequence whose nth term is the product of the nth terms, is just the product of the limits. So, I can think of this product here as just being, there are two sequences, one of them is an, the other is an plus 1, just shifted by 1. And so, I can think of this as just the limit of an plus 1 times the limit of an. And on the right hand side, it is of course 1 plus an. And now we are ready to substitute. The limit we assumed was the number L, and on the right hand side it is 1 plus L. So, what this gives us is an equation for L. It tells us that L square minus L minus 1 is 0, and the roots of this quadratic equation are 1 plus or minus square root of 5 by 2, and observe that the negative solution minus square root 5 by 2 is not possible because all the an's are positive. So, recall that an is just the quotient of two successive Fibonacci numbers. So, an's are in fact all positive numbers. Therefore, the limit can't be negative. So, the limit of an is 0 or more, it is greater than or equal to 0. Therefore, the only possible solution we can choose is 1 plus square root 5 by 2. Okay. So, that is in fact what the Fibonacci ratios tend towards. This is called the golden ratio. Okay. And if you actually compute it, it is something like 1.618 whatever. So, up to 3 decimal places it is 1.618. Okay. So, of course, we did all this under the assumption that the limit exists, right. So, that was our proposition that the limit actually exists. So, here is the question, why does the limit exist? So, to answer this, we will use the observation we made that if you really look at this graph of the terms, they sort of oscillate, right, and in fact the odd and the evens seem to the even terms seem to be decreasing in size, the odd terms seem to be increasing in size. So, let us write these out as these observations out as claims. So, recall I defined the nth term, the nth ratio as fn plus 1 over fn. So, let us say we start from n equals 1. So, I first start with f2 over f1. Then here is my proposition or claim, proposition A135. So, okay, maybe we should also take A0 so that I have the evens to match up with that picture. So, if I look at the odds A1, A3, A5, so they decrease in size, in fact they are all strictly smaller, A1 greater than A3 greater than A5, and the evens are go the other way. So, A0, 2, 4, etc. Okay. So, this is the first observation. So, here is observation 1. Observation 2 is that all these ANs are bounded. So, they are all numbers between 1 and 2, all these successive ratios. Okay. So, what would these give us if claims 1 and 2, if this proposition actually holds, then it tells us that what we are looking at are these two sequences of the odd A's and the even A's. They both live between 1 and 2. So, here is 2 and 1, and let us say I plot the even A's, A0, A2 and so on. So, they sort of increase, they form an increasing sequence. So, I do not quite know where they go, but they form an increasing bounded sequence. Likewise, the other sequence, the A1s, they form sort of a decreasing bounded sequence. And what we are trying to show is that eventually these two sequences converge to the same limit. This we did, right, Amri? Bounded monotonic? Yeah. Okay. So recall the following theorem which we will use. A bounded monotonic sequence always converges. Okay, so let's again do the following. Let's assume this proposition for the moment, that we know that the odds and the even ratios are both monotonic. One is monotonic decreasing, the other is monotonic increasing, and that they are all bounded between 1 and 2. And assuming this, we have the following consequence. Hence, the odds certainly converge. Limit a to k as k goes to infinity certainly exists, and likewise the evens converge, and likewise the odds converge. So this is our conclusion. Okay, and maybe let's call these guys something, the limit L even and the limit L odd, and what we really are trying to show is that these two numbers are the same. Okay, that the even and the odd limits are equal. So if we sort of go back and see how we computed this golden ratio, so this was the equation we used, that this product of limits is 1 plus an. So let's just tweak this a little bit. So if you sort of look at this very same equation here, I am just going to write it with n equals 2k. So let's just rewrite this equation, but let's put n equals 2k here. So let's rewrite as follows. I am going to put a 2k plus 1 and a 2k equals 1 plus a 2k. Okay, and now we will do the same thing. We will take limits on both sides of this equation. So at the moment I am only applying it to the case when n is even, but that is already enough. Now we just apply limits. So let's look at limit as k goes to infinity of the left hand side equals limit k goes to infinity of the right hand side. Okay, and now the left hand side becomes L odd times L even, whereas the right hand side is 1 plus L even. Okay, so that's the conclusion we make. Now what does this tell us? This tells us, I mean this is if you put n to be even. So we have that both these limits exist, and our task now is to show that these two limits are the same. Okay, now to do this, let's recall the equation that we had earlier, which is the following, that an times an plus 1 is 1 plus an. Okay, now we will just split this up into two separate cases. We will just take n odd and n even. So if you take n odd, this is like, or let's say take n even, let's put n equals 2k, we can think of it like this. So that's one case. Or you can take n to be 2k plus 1. This is 2k plus 2, a 2k plus 1. So I have just split this original equation into two separate cases for n odd and n even, and now the goal is to do what we did earlier. We will just still do the same thing. We will take limit, well in this case k goes to infinity of this equation equals limit k goes to infinity here. Okay. Now what does that give us? Now it splits into two parts. The limit k goes to infinity of the first term is L odd, limit k goes to infinity of the second term is L even, whereas the right hand side gives me 1 plus L even. Now I could do the same thing here, take limits on both sides, and I would get L even times L odd equals 1 plus L odd. Okay, so what I have really are two equations now. Earlier when we tried to compute the limit, we just had, we thought of everything as L, we assumed the limit exists, and then we were able to get a single equation. Now there are two separate limits which we know do exist, and there is some equations which connect both of them. Okay, and these are the two equations. So the first equation tells me this is just 1 plus so L0 or LO. यहाँ से I'm just going to compute LE is 1 plus 1 over LO. Yes, sorry. Now from the second equation, I replace LE by 1 plus 1 over LO. Okay. So what I have is that LO equals 1 over 1 plus 1 over LO, and you just have to unravel what this means. If you do that, you get the following equation. You get that LO equals 2LO plus 1 over LO plus 1, or if you expand both sides and so on, you get LO squared minus LO minus 1 is 0. Okay. Likewise, if you do the same thing with LE, or you can use the equation which connects them, likewise you conclude the same thing about LE, that it also satisfies the same equation. Okay, and from this, by using the same analysis as before, that it's a sequence of positive terms, you conclude that both of these must actually equal the golden ratio. So this is one way of sort of observing that the ratio of the successive Fibonacci's tends towards the golden ratio. And here we have used the fact that a monotonic bounded sequence always converges. Okay, so we are still down to proving this fact here, that the odd ratios decrease in value and the even ratios are monotonically increasing. So let me just sort of point you to how we would do this, and maybe leave the main details to you as an exercise. So the Fibonacci's have this very interesting property. If you write the first few out, you will notice a certain oscillatory behavior, 21 and so on. When you try to compute the following, you take any three successive terms. So for example, you take these three successive terms, you take the square of the middle term and minus the product of the two outer terms. So in this case, the outer terms are 1 and 3, and 2 square minus 1 into 3 is 1. Okay. Now if you take the next three terms, so 2, 3 and 5, then that's 3 squared minus 5 into 2, that's 9 minus 10, that's now a minus 1. So whereas this was a 1, the next is a minus 1. Now the next three terms would give you 5 squared minus 8 3s are 24, so 25 minus 24 is plus 1. The next three give you 64 minus 65, which is minus 1, and so on. So the following is the little lemma that sort of tells you where this oscillatory sort of behavior comes from. It says if you look at fn plus 1 squared, or maybe let us say fn squared minus n minus 1 n plus 1, this is just minus 1 power n. Okay, so I am going to leave the proof to you guys. This is just a simple proof by induction. Okay, so it's just you compute the n plus 1th term and you will find that you can just use the definition of the Fibonacci's, and the n plus 1th term will turn out to be negative of the nth term. Okay, now that's the key thing that one needs to prove the proposition. So the proof of the proposition here. So again, let me give you the main idea. So the proof of proposition. So what we needed to prove is that A1 is bigger than A3 is bigger than A5 and so on. F4 by F2, A5 is
F4 by F3.
Oh, yeah. So A3 by definition is F4 by F3, A5 by definition is F6 by F5. Okay, now we need to compare A5 with A3. So let's start with A5 and try to somehow bring A3 into the picture. So this is F6, F5, and we will use the Fibonacci relation to write F6 as F5 plus F4, 4 plus 3. But we want to sort of go one more step. So I also want to change the 5 to a 4 because I am only comparing A5 with A3. So this is actually, I'll also rewrite this F5 again in terms of F4 and 3 becomes this, and this becomes 2F3 plus F2. Okay, and now notice that this is actually the following. From the first term, I will take out F4, and from the denominator I will pull out an F3. So this is actually F4 by F3 times the following. It's 2 plus F3 over F4 and 2 plus F2 over F3. Okay, and now we are in business, because if you notice F4 by F3 is exactly your A4, right? Sorry, A3. So on the left hand side I have A5, on the right hand side my first term is an A3, and I have an extra term which I have to analyze. Okay, but observe that this extra term is, well, what is it? It's actually a numerator over denominator, and I claim that the numerator is smaller than the denominator. Okay, so let's check what was the numerator. It was 2 plus F3 over 4. The denominator is 2 plus F2 over F3. So I claim that the term on the top, F3 over F4, is actually smaller than F2 over F3. Okay, and why is this? Well, this was the lemma that we talked about. If you looked at F3 squared minus F2 F4, the Fibonacci square of the third term minus 2 times 4, that's in fact minus 1 power n. So this is actually minus 1 power 3 in this case, right? So in other words, F3 squared is smaller than F2 F4. I mean, one can actually check, of course. So it's 1 1 2 3, so it's 3 squared, and then this is 2 into 5. Okay, but the same proof works in general. So you could just do the very same thing in general with any two successive odd terms. So what I am trying to say here is that the numerator is smaller than the denominator, so this additional fraction is smaller than 1, and that's basically what we needed to prove. So this is therefore smaller than A3. So this is really the proof for the first two terms, that A5 is actually smaller than A3, but you can just adapt this proof and prove in general that A2n plus 1 is smaller than A2n minus 1. And if you try doing this with the even terms instead of the odd terms, you will find the other oscillatory product. Instead of an odd Fibonacci squared minus the product of its neighbors, you will find an even Fibonacci squared minus the product of its neighbors. So there the inequality will just reverse. Okay, so a lot of this this behavior that we are saying really comes from this basic observation. Okay, good. So we are we've shown that, well, at least I hope you can complete this argument to show that the proposition holds. So let's go back to the statement of the proposition. So I'm going to leave this for you guys to complete, and let's just quickly see why this is true. An is bounded. An lies between 1 and 2. Okay, so what is An? It's the quotient of, so this is the boundedness of An. An was Fn plus 1 over Fn. So of course the n plus 1th Fibonacci number is more than the nth one, so this is in fact strictly greater than 1. But observe that the n plus 1th Fibonacci number is in fact Fn plus Fn minus 1, which is at most 2 times Fn, for the same reason that Fn minus 1 is smaller than Fn. And so if you divide, the answer is at most 2. Okay, so that completes the proof of the boundedness. So what we have done really is shown that the successive ratio of Fibonacci's can be viewed as two interlacing sequences. So, one which sort of decreases, the other which increases, but both of them converge to the same limit, which is the golden ratio. So, that completes the proof.